Good afternoon, everyone. So, there has been some queries regarding the allocation of project work. So, I hope you can see this PDF file, and I will just clarify some of the issues. So, in the assignment in this PDF file, you will find some arrangements or permutation combinations of rather combinations of different problems. So, how to read the assignment, that means how to carry out the project. First, with the set of equations Gj, that is some number G1, G2, and using the pressure equation Pj, the stretching Sj, we make the perturbation expansion Ej and obtain the dispersion relation or KdV Burgess, or the dispersion relation and KdV Burgess equation, or even the Sag-Div equation, whatever it is, and study the parametric variations graphically. Now, let's carry out these things. So there are three levels. Level 1, and this easy level till project number 48. 49 to 96 is moderate, and 97 to 192, that is 96 problems, they are a bit laborious but easy. You see, this has been typed twice. Okay, so you see there's a Sag-Div pseudo-potential approach that's been included here. Well, come here first. So you see this dr, g1, p1, s1, e1 plot. That means you have to find the dispersion relation using the governing equations set g1 with perturbation expansion p1, stretching s1, e1 is the it is the equation of state p1 and the perturbation expansion e1, and finally we get the equation in plot. Now how to read these things? So many problems are given here. Now you see this is G1, that is you have to start with these governing equations. So it's an electron acoustic mode. You see hot electrons or cold electrons. Hot electrons have no inertia, cold electrons have no pressure term. They have viscous term. However, those who will do KdV, they will eliminate this term. Those who will do KdV Burgess, they have to include this term. Okay, and for the normalization and all these conditions, you just refer to one of our papers that will be given along with. Okay, now coming to the ion acoustic mode, you see there are two ways of solving. For instance, these are the 5 equations. Okay, for ion momentum equation, electron momentum equation, ion continuity, electron continuity, and Pauli's equation. So you see, if you take the ions equation only, that is this equation, and the Pauli's equation, and in place of the electron density, you take some distribution, be it Maxwellian or some Kappa distributed, whatever, it depends upon you. If you carry out with those things, you can get ion acoustic mode, or else you can get electrostatic mode, where you have to take these 5 equations, and this is the set of equation is given by G2. Okay, similarly you have something for a classical plasma is G3. It's in this part. You see, this is dust acoustic mode. You have got the dust equations, the ion equation, and the electron equation. Electron has got the quantum effect. Now these are the, I will provide you with the normalization schemes. Now, as I have said that there has been different conditions regarding this pressure. Now you may take the pressure to be Fermi kind of thing according to your combination. If it is P1, if it is P2, you can take it for the relativistic degeneracy. Okay, and if you go for a third law, that is ultra relativistic degeneracy pressure, where you can use this term only. Okay, this is the longer term, with this is simplified with this term. Similarly, it is also simplified into this thing. Now it's up to you if you want to carry out with this big expression or the simplified one. That's up to you. Now you can take This is another pressure law is for the classical particles. Suppose you consider classical ions and quantum electrons in a system of equations. For instance, suppose this expression. Here the ions may be considered classical and the electrons may be considered quantum. So a combination of this classical pressure for ions and the quantum pressure, that is P1 for the electrons. You can make a combination. Now it's up to you how you will normalize. That is your expertise. Now you can use the stretching as this kind of stretching, epsilon to the power half, epsilon 3 by 2, or epsilon q. There are two kinds of stretching. As per your problem, project problem, you have to choose S1 or S2. Similarly, for the perturbation expansion E1, you have got this expression. You see, Nj, that is for electron or ion or dust, whatever it is, or hot electron, cold electron, this would be the perturbation expansions in the normalized case. And it is another perturbation expansion where you will have the odd powers only. You see, epsilon 1, epsilon q, epsilon 5. Here it was all odd and even powers, but it is odd. It is odd and even, it is only odd. Okay. And we have not taken only even because that would again amount to this thing only. Okay. Now in many of the problems you may apply some of the particle distributions, as I have said. So it is a Q non-extensive distribution. It's called Q non-extensive distribution. This is a kappa distribution. For this, if you can search the internet, that's up to you. And it's a Maxwell distribution. So these are the kind of problems. Now let me sum up once again. These are the different problems with different combinations. What the first one is the target that you have to carry out with this G1 or G2 governing equation, P1 the pressure law, the stretching, and the perturbation expansion, and finally plot. Now some of you, well, these are the set of equations. You will start with G1 if you are starting with G1, if it is G2, if it is G3. Remember, if you are doing a G1, it would be electron acoustic mode. If you are doing a G2, it is ion acoustic mode, and it is dust acoustic mode. Now I have given the papers for reference, and here are the pressure laws. You see, pressure laws that you can use, and you can also find all these papers in the papers for reference folder in the classroom. Okay, so these are the different kinds of stretchings you may use as per your S1, S2, and these are the perturbation expansions. Now some of you have asked, sir, we want to do astrophysical plasma. Well, once you are done with it, you can extend it to your astrophysical plasma, those who want to do it. For instance, if anyone is willing to study the shock waves in magnetospheric sheets, so they have to take the KdV Barger's equation. If someone is willing to carry out the study of solitary profile or solitons propagation in space plasma, then they have to do KdV equation. If someone is willing to study the instability, then from the KdV equation or KdV Barger's equation, one can give a transformation to a log wave kind of solution. So that's the later part. First you have to do these things, and those who are very much dedicated to go for astrophysical plasma, I have told some of them, and I would like to say you again that once you come up with the KdV Barger's equation, we can, or KdV equation, you can also study the different kind of instability, or even with the dispersion relation, you can carry out the instability study, that is two stream instability, Rayleigh-Taylor instability, and with the log wave you can study the modulation instability, this kind of thing. So I hope I am clear with the assignment. Thank you.